In understanding anything, it is the context that best sheds light on the thing. The description is the skeleton. A better understanding of the specificity of derivatives is essential to harnessing them in decision-making. We will explore an example to illustrate how derivatives are uniquely contextual. This case study on derivatives explores their different meanings and complexities. The example is that of the rate of chemical reactions. Understanding the complexities of rate of chemical reactions is very important for grasping the idea of derivatives. Chemical reaction rate and its instantaneous values. In a chemical reaction, one or more reactants interact to produce one or more products. The chemical reaction rate measures how quickly a chemical reaction occurs. It is typically expressed as the change in the concentration of either a reactant or a product over a specified period of time. Key factors affecting chemical reactions: concentration of the reactants, temperature, pressure, presence of a catalyst, surface area of the reactants, for example, powdered or rocks of reactants. Chemical reactions are optimized for viable chemical production processes by increasing the yield of the desired product, reduces the amount of reactants needed, thereby lowering the cost of raw materials and other inputs like catalysts, energy for raising or lowering temperature and pressure, etc., meeting the regulatory requirements for safety, quality, and environmental impact. Reducing the amount of waste generated is also a goal. Improving product quality and process efficiency, etc. How to optimize chemical reactions. The best axis for optimization of chemical reactions is monitoring closely and influencing the rate of chemical reaction. The rate of a chemical reaction can be optimized by fine-tuning the reaction conditions, such as temperature, pressure, reactant concentration, using a catalyst, mixing of reactants, etc. The rate best determines the outcome of the reaction, how much product will be formed and how quickly it will be formed. How do we fine-tune reaction conditions? Fine-tuning reaction conditions involves quantifying and mathematizing the mechanisms that govern the interaction of compounds and elements in chemical reactions. Laws of chemistry are just as precise as the laws of physics and are expressed in quantitative expressions. The principles of chemistry are as rigorously defined as those of physics and are expressed using precise quantitative expressions. The rate of chemical reactions is mathematically expressed using the rate law equation. The rate law expresses the rate of a chemical reaction as a function of the concentrations of the reactants, catalysts, and other factors involved in the reaction. The rate law for each reaction is derived from experimental observations, usually by measuring the reaction rate at various concentrations of the reactants and other factors. For a reaction involving reactants A and B, it is expressed as rates is equal to K times A to power M into B to the power N, where K is the rate constant. A and B are the concentrations of reactants A and B. M and N are the reaction orders with respect to A and B. Finding the rate constant. Every reaction has its rate constant, a number, which is experimentally determined. Recall that the rate law includes only the concentration of the reactants. All other factors affecting the rate of reaction are represented by the rate constant. The rate constant acts as a multiplier to the rate of reaction determined by the concentration of the reactants. For instance, factors like temperature influence the specific value of the rate constant for a reaction. Significance of reaction orders. Reaction orders indicate how the rate of the reaction depends on the concentration of each reactant. In zero-order reaction, M equal to 0 and N equal to 0, then rate of the reaction is independent of the concentrations of the reactants. In first-order reaction, M equal to 1 and N equal to 1, then the rate of the reaction is directly proportional to the concentrations of the reactants. If the reaction is first order with respect to one reactant and zero order with respect to another reactant, that is, m equal to 1 and n equal to 0, then an increase in the concentration of the first reactant increases the rate of the reaction, while an increase in the concentration of the second reactant does not affect the rate of reaction. Derivative of rate law with respect to a particular reactant concentration. The derivative of the rate law equation with respect to a particular reactant concentration gives the reaction order with respect to that reactant. This derivative measures how the rate of the reaction changes, with variations in the concentration of that specific reactant. It applies to the entire reaction over its entire duration. It is a generic characterization of the reaction. Derivative of rate law with respect to other features. It is important to note that the effects of catalysts, temperature, pressure, and reaction orders on a chemical reaction can be complex. Optimizing the reaction conditions may require careful experimentation and analysis. Why is instantaneous derivative needed, and it is more precise than the rate law derivative? The derivative of the rate law alone does not provide enough detail for precise adjustments to the reaction conditions. This can result in suboptimal reaction conditions, where the chemical reaction is not occurring at its highest possible efficiency or productivity, leading to lower yields or selectivity. The instantaneous derivative of the rate law provides information about how the rate of reaction precisely changes. This derivative often involves taking the derivative of the rate law with respect to time or with respect to the concentration of a reactant. This information allows for more precise adjustments to the reaction conditions to achieve the desired outcome. The instantaneous rate of chemical reaction is the instantaneous derivative of the rate law. It specifically refers to the derivative evaluated at a particular instant in time or at a specific concentration point. This derivative is about the nature of a reaction under very specific conditions or instants. It could well be extended to any specific value of the reaction's conditions. For instance, it is this rate that can illuminate us on the effect of the use of catalysts on the way concentration of reactants or products may be changing over time. Monitoring the instantaneous rate is crucial for determining the amounts of products and reactants and for controlling other reaction conditions. Example of the need of instantaneous rate of chemical reaction. During some chemical reactions, high energy can be released, generating significant amounts of heat. Monitoring the instantaneous rate of the reaction allows for early detection of any potential runaway reactions, helping to prevent unsafe incidents. This example is deliberately extreme to show the extent of the significance of instantaneous rate of reactions. This case study is to showcase the special importance of the instantaneous derivative of the rate law. The one, overall derivative of the rate law is only a broad indicator of the nature of a reaction. For sure, the basic nature of a chemical reaction, what we call stoichiometry, is mostly unaffected by the change of conditions. I hope this case study added to the understanding of the idea of derivatives in general and as instantaneous values. The idea of the measure of the change of something at specific instants or any specific other conditions is also a matter of how deeply we know any continuous change, or how much we wish to know to control continuous change. For example, in this case study, we noticed how the instantaneous derivative of the rate expands our ability to study the effect of all other conditions too, beyond the concentration of reactants. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.